All right. Well, good morning or good afternoon, everyone. We're looking at a new identity today. We're going to look at the proof of one of them. There's 4 new identities called the sum and difference formulas. This is in chapter 10.4. The formula itself is simple enough. We'll start off with just writing one of them. The formula says that if you take cosine of one angle plus a different angle, like this. Actually, we're gonna do cosine of u minus v. Then this is equal to cosine of u times cosine of v minus plus sine of u times sine of v. Now the reason we use u and v are they're just used as angles. There's no real need to use u and v, but typically we use those when we talk about vectors. So we're using u and v for these formulas as they're used in vectors. We're not going to be talking about that anytime soon, but this is what we have. Cosine of u minus v is equal to cosine of u times cosine of v plus sine of u times sine of v. We could just take this and run with it and start using it. What this means, if we had something like cosine of, let's get a good angle. Cosine of 105 degrees. We could actually find this angle using this difference formula. So the reason we can do that is we can take u and v to be values that we know to equal 105. So a value that we know for u and a value that we know for v, and then subtract them. So what can we use here? Well, if we had 150 degrees minus 45, that would work. Right, this is the same as 150 degrees minus 45 degrees. So that's an option. And once we have this, then we're just saying that u is equal to 150 degrees and v is equal to 45 degrees. And then we plug them into our formula. So cosine of 150 times cosine of 45 plus sine of 150 times sine of 45. So we would know that cosine of 105 is equal to all this multiplied out with our common angles. All right, these are angles that we could find using our unit circle, but we don't know what 105 degrees is using our unit circle. But we would know it's equal to this, so we can solve this out. So cosine of 150, that's going to be negative square root of 3 over 2. It's going to be multiplied times cosine of 45, which is square root of 2 over 2. And we have plus, see the y value here would be 1/2 at 150, multiplied times, see the square root of 2 over 2 again. So we would get that our answer is the square root of 6 over 4 plus the square root of 2 over 4. So that cosine of 105 degrees is equal to the square root of 2 minus the square root of 6 over 4. So it is equal to a fraction here. This is a irrational number, but it is a decimal that's that we can find as represented by radical values, right? Square root of 2 and square root of 6 radical values. So this is good. We can use these formulas to find angles that we normally wouldn't be able to find. And this means that we can add a whole bunch of angles to our list of angles that we can find actual values for. So for instance, if we take any multiple of 45 and any multiple, let's say plus or minus 45, and any multiple of 45 here, let's call it m, right? Then we can find the x or y values at those angles on the unit circle. So I guess yeah, this would work. So we're N and M are just some whole numbers. So for instance, if we took 45 minus 30, right, that's just 45 times 1 minus 30 times 1. That's 15 degrees. So we could find the x or y value at 15 degrees using these formulas. We could find, let's see, we could take 90 or 135 minus 30. We just did that, 105. Take, we could find the degree of 135 or 165 or 195, right? And eventually we'll find that really we can find the degree value of any multiple of 15 degrees. Right, so now we can find 15, 30, 45, 60, 75, 90, 105, 120, 135, 150, 165, and so on. You can find actual values as represented by a fraction of radical numbers and normal rational numbers. All right, so, but how do we know that this is true? How do we know that this formula holds, and what does it really mean? Well, this is something that we're going to look at geometrically using our unit circle. There is a document that I will have posted on Google Classroom by the time I've posted this video that you can look at for notes and kind of follow along while looking at this problem. So what we're going to try and do is show a problem where we have an angle of u minus v, right? And we're going to try and show that the cosine of that angle, or really that's talking about the x value, is equal to the x value of just angle u times the x value of just angle v plus the y value of u and y value of v. So to start off, we need to have a unit circle. So actually, let me get a piece of paper. Okay, so to start off, we're gonna have a unit circle. And we're gonna start with one of our points on our circle right here at 1, 0. Right, the unit circle has a radius of 1, no matter where you start from the center. And these are going to be our axes here. We've got our x-axis, our y-axis, and we're going to start off saying that we're going to start with 4 points, A, B, C, and D. All right, we're going to let point A be right here at 1, 0. So we're going to say let A be equal to 1, 0. We're going to let B just be somewhere over here. And the coordinate is going to be unknown. So we're just going to say it has coordinates we'll call it x1, comma, y1. All right. So B is going to be equal to x1, comma, y1. And we're going to say that we have placed B exactly so that this angle here is of value V. So it's V degrees. Okay. For points, we're going to skip all the way to point D. Point D we'll call x3, comma, y3. It's again just two values that we just don't know what they are. We'll say it's over here. And we're going to draw it so it's exactly u degrees. So this big distance here, not distance, the angle here is u degrees. All right, so for point C is going to be the spot in between B and D, where it is equal to the angle u subtracted by the angle v. So let's say it's about right here. So we'll say it's point C, and for it too, we're just going to say that its coordinates x2, comma, y2. Right? We don't know exactly what these coordinates are. So this is the spot where we've taken angle u and subtracted angle v. So let's see where to draw this here. This is u minus v. oops, this distance, this angle, I mean. And what's also going to be true, if this is u minus v, then this angle here is also u minus v, the angle from D to B. Now, the reason for that is if this whole thing is angle u, right, and this is u minus v, then this spot has to be v, because that would mean that v plus u minus v is equal to u, which was this big angle in the first place. So if this is v, and this is u minus v, but this is angle v, then u minus v plus v has to be angle u. Right, so we would get that this angle CA has to be u minus v, and angle BD has to be equal to u minus v. Now, if that is confusing to you, maybe redraw your circle and think about why that has to be true. So if this is angle V, here's angle U again. Right, this big distance is angle U. Right, and we're finding a spot that is equal to u minus v, a line. Right, if this whole thing is angle u, then we take off v. We can either cut off this part as being v, and we're just considering from this line to that line as being angle u minus v, or we can chop off v on the other side of this dashed line, right? And this part here would have to be angle v, and now we've taken our whole angle u, subtracted v. So there's two ways that we can get u minus v, from our line here to our x-axis, or from the line for D to the line for B. So we will say angle DB has to be equal to u minus v degrees, but also angle AC has to be equal to u minus v degrees. Okay, so this is good. We have a way to talk about u minus v as an angle, and we want to do that because what we're trying to prove is that the cosine of u minus v is equal to cosine of u times cosine of v plus sine of u times sine of v, right? Which is the x coordinate of u minus v, right? Which should be x2 here. And I'm talking about the other coordinates of these 4 points that we've been talking about, which are representative of angle v and angle u independently. So we're trying to show that this is equal to cosine of u times cosine of v plus sine of u times sine of v. So one thing we're going to use here to create a little formula is we're going to use the formula for an arc, right? That says that the arc length is equal to the radius of a circle times an angle, or S is equal to the radius times an angle, right? Arc length, and here we have radius, and here's our angle. Okay, so if we look at, let's say, angle AC, right? For angle AC, that angle is u minus v. So we'd have that angle is equal to u minus v. The radius is 1, no matter what we're doing here. So that means if we're solving for the arc length, right, that S has to be equal to, well, the radius times u minus v. U minus v times 1. Well, anything times 1 is itself, so the arc length is the same as the angle for the unit circle, right? It's a special property of the unit circle that makes, that's very cool. The arc length is always equal to the angle because the radius is 1. So if this arc length is equal to u minus v, what we're also going to find is that the arc length of dB is also equal to u minus v, because the angle is the same and the radius is the same, therefore the arc length is the same. So if this arc length is equal to this arc length, we also know that the distances between the 2 points are the same, right? That is a property of chords on a circle. Chords being a point on a circle to another point in the circle, as long as they're not diameters, not going through the center of the circle. So we would say by properties of a circle, we would know that AC, the distance, is equal to BD. All right. Well, one thing we did earlier last semester was using the distance formula. So we're going to use the distance formula to create a little equation here. We've got our equation. We're going to try to make it look like this equation here that we're trying to prove. So for AC, we're going to think about our distance formula. A distance formula says that the distance between 2 points is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. The square root of the differences of the x values and the y values of the two different points. So if we're thinking of AC, it doesn't really matter whether we make C be the first point or the second point. This little process here is finding the difference and then squaring it is going to guarantee that if we have x1 minus x2 squared or x2 minus x1 squared, it's going to be the same value because that negative value will go away when we square it. So we just have to pick one point. So let's say that our y2 is C. All right, so for C, we're just going to take our value here of x2, we just leave it as is. And for x1, we actually know those numbers, right? x1 is going to be 1 because it's at the point 1, 0 for A. So minus 1 squared. And our y values is just y2 for C minus the y value here, which is 0 squared. All right, and that's the distance of that line. We're going to use the same distance formula for dB. We're going to say that, let's just use x3 and y3 as our first coordinate. So we have x3 minus x1, that's the x value of b squared, plus y3 minus y1 squared. Okay, and we're going to try to simplify this. Now, the left side is going to be more easy to simplify. The right side, a little more tricky. One thing we can do right away is we can get rid of these square roots, right? These are both just raised to the 1/2 power. So we can get rid of those quickly by squaring both sides, right? A little square, you can think of those as canceling. And we're left with x squared minus 1 squared plus y2 minus 0 squared is equal to x cubed minus x1 squared plus y cubed minus y1 squared. Let's simplify this left side a little bit, and we're going to simplify the right side as well. So for x squared minus 1 squared, we will get an an x2 squared term. The difference between subscripts and superscripts is important here. We'll have a minus 2x2, and we'll get a plus 1. For this one, it's pretty easy. Y squared minus 0 squared is just y squared squared. Right? There's nothing to distribute. There's no FOIL to do here, really. So plus y2 squared. And then for our right side, we do have to use some distribution properties. We'll get an x base 3 squared minus 2x1 x3 minus x1 squared. And the y's will look similar. We'll have a y subscript of 3, y3 squared minus 2y1 y3 plus y1 squared. Okay. Well, what can we simplify here? Oops, I did this wrong. This should be a plus sign here, right? Because minus x1 times minus x1 is positive x1 squared. Well, one thing that we're going to use is, right our definition of our unit circle here, right? For a unit circle, the graph of this, it says that if we take x squared plus y squared, that is equal to 1. That is the graph of a unit circle, right? Now, if we have different points of a coordinate on a circle, like x2 and y2, it should also be true that we take this x coordinate and we square it plus the y coordinate and square it, that is equal to 1. For instance, let's look at one of the coordinates on our unit circle that we know, right? How about the square root of 2 over 2 and the square root of 2 over 2, right? We know that that coordinate is at 45 degrees. Okay, well, is it true that if we square the first coordinate and we square the second coordinate, that is equal to 1? Well, let's see. We would get 2 over 4 plus 2 over 4 is equal to 1, which is 4 over 4. So it works out for this coordinate, and it will work out for all other coordinates on the unit circle. So in case of our formula here, if we have any place where we have an x2 and a y2, we know that that is actually equal to 1. So let's group those. We have x2 squared plus y2 squared. We'll group it like that. You have that minus 2x2 and a little extra plus 1 on the end. And then over here we have a y1 squared and x1 squared. And also a y3 squared and an x3 squared. x3 squared plus y3 squared. And we have our middle terms here, the minus 2 x1 x3 and minus 2 y1 y3. So all of these little parentheses here should be equal to 1, right? Because we're on the unit circle, which makes things a lot easier. So this becomes 1, minus 2 x2 plus 1, and we have 2 1s here, so 1 plus 1 is going to be 2. Just add those together, minus 2 x1 x3 minus 2 y1 y3. 1 plus 1 here, we can simplify that. So we have 2 minus 2 x2 is equal to 2 minus 2 x1 x3 minus 2 y1 y3. All right, so think about what you might do here at this point. What's something common these all have? Well, I have 2 as a coefficient. Right, so we can divide everything by 2, and it's all just reduced to coefficients of 1. Okay, now we also have 2 1s on both sides. We can get rid of those. Subtracting 1 on both sides. And lastly, we can simplify this expression by dividing both sides by -1. I'm running out of paper, so I'm going to have a new sheet. So we have that x2 is equal to x1 x3 plus y1 y3. Well, what do we do from here? There's certainly nothing we can do that can simplify these x's in some ways, but it might help to look at what we were trying to prove in the first place. We were trying to prove that cosine of u minus v is equal to cosine of u times cosine of v plus sine of u sine of v. All right, well, these are starting to look pretty similar, but how do we know that we can convert from here to there? Well, to do that, we're gonna have to look at a picture again. So, of our picture right here, the angle u minus v, well, one of them, the x-coordinate is x2. So if we want to think about what this means in terms of cosine, we are saying that the x-coordinate of the angle u minus v is x2, right? These are the same thing. Cosine of u minus v is just talking about the x-coordinate at this angle. So we can substitute x2 for cosine of u minus v. And similarly, these other x values and y values are just talking about the x value at that angle, the angle that it corresponds to on our circle here. So for instance, x1 corresponds to angle v. Right? It's a little bit hidden, but that was our angle v, the smallest angle here. Right? So if x1 is the x value of angle v, we're saying that it's equal to cosine of angle v. And similarly, x3 is cosine of angle u. Plus, well, for y values, we're talking about the sine of the angle. So for y1, the angle is v, so we want to look at the y value at that coordinate represented by angle v, which is y1. So that would be sine of v. And similarly, sine of u. This big angle is angle u, right? And there we have it. We have our formula. Now, properties of association tells us that we could flip those since they're multiplied, right? 3 times 7 is the same as 7 times 3. So we could just rewrite this as cosine of u times cosine of v plus sine of u times sine of v. At that point, we would have proved our little proof here that we've been doing. Now, there are 3 other sum and difference formulas, which we will not be doing proofs for directly because they're all going to be very similar. You can imagine us setting up a u minus v angle for sine and then just thinking about the y coordinates instead. We can do a very quick proof of cosine of u plus v. To figure out what this identity is, we can just use our previous identity that we just solved. So cosine of u plus v is the same as cosine of u minus v. Right? If we were to distribute that minus 1, we'd get back to u plus v. So we can use this formula right here as long as we just substitute in minus v everywhere we get v. All right, so cosine of u is the same, right? There's no v's there. Cosine of minus v, we have a sine of u and a sine of minus v now. Well, how do we know what cosine minus v is? Well, this is going back and using our even or odd identities, right? Still using these guys. And those identities say that if we take cosine of, say, negative 45 degrees, think about our unit circle. Let's see, negative 45 is right there, right? And we want the x value here. What is our x value? Well, the x value would be square root of 2 over 2. And when we looked at these before, we observed that if we took cosine of 45 degrees to the positive, that it's also the square root of 2 over 2, right? X is the same positive number for cosine. So if that's true, we can just say, I don't want to think about it in terms of minus v, since it's the same as cosine of positive v. However, for sine of minus v, if we look at, I'm going to draw another unit circle. Let's look at sine of 30 degrees and sine of minus 30 degrees. Well, here our y value would be positive 1/2, but also negative 1/2 here, right? It's going below the y-axis, so it becomes negative. So these are not the same, but it is true that sine of 30 degrees is really just the negative of sine of negative 30 degrees, right? So we will get that if we convert sine of negative v to sine of positive v, we just have to pull out a negative sign here. Sine of u times sine of positive v to account for that change. So if you've forgotten these, make sure you review even or odd identities. Right, and that is just a quick proof of what cosine of u plus v is, right? It's the same thing for cosine of u and cosine of v, but now our sign changes. For sine of u plus v, and also sine of u minus v, for both of these, we'll get something slightly different. For these, our answer will be that they're equal to sine of u times cosine of v minus cosine of u sine of v. And for this, sine of u times cosine of v plus cosine of u sine of v. Right? The proofs for these will be similar, but we won't be looking at them. So here's one. Our second one. Uh-oh. That's not good. Our third and fourth. Well, that's a little messy. I'll rewrite them here, and then that'll be it. So these are 4 new identities. They're called the sum and difference formulas, which we'll be using in new problems and practicing. The next homework that we will do will be using these problems both to do problems like this, right? Figuring out what the x value of 1 and 5 is, but also simplification problems, right? If you have cosine u minus v, you could rewrite it as that, and maybe simplify more easily from there. So this is cosine of u, cosine of v, plus sine of u times sine of v. For this one, we just change the sign in the middle. And for the sine ones, the sign is always the opposite. That's how I remember it. And you always have cosine and sine switching, right? Sine, cosine, and then cosine, sine. But the u and v stay in the same place. Sine of u, cosine of v, minus cosine of u, sine of v. There we go.